and traction motor, transformer, battery, and bogie. So these are some of the equipments in the underframe of loco. We will see only these important components or the equipments. In addition to that, I will also talk about auxiliary machines and the auxiliary motors that we have in the locomotive, and the other smaller components and the equipments which are available in the locomotive. I'm not going to touch them per se, because neither the time permits to cover all of them, nor it is required for the foundation program that we should be covered. So let's restrict our discussion only to some of the major components or the equipments which take very important role or which play a very important role in the overall working of the locomotive. The pantograph is the most visible equipment or the component that we have on loco. It collects the current from contact wire for the electric locomotive, and we have a pantopan, which is the topmost portion on the pantograph, which remains in contact with the contact wire for the purpose of collection of the current. The pantograph pan or pentopan, as it is known, it has two strips made up of carbon graphite. The purpose of making it a softer material is simple, in a way that whenever we have a continuous rubbing of two metal bodies, the material or the equipment which is of a softer material, it will start reducing in size, because there will be constant wear and tear on the component which has a softer material for its constitution. Here, when we decided to have pantograph pan, we had both the options available to us, whether to have the whether to use softer material for the pantograph pan or to use softer material for the contact wire. The option was then decided in favor of pantograph pan to be made of softer material, because I can change these pantograph strips during the attention that we pay in the trip sheet. So it's easy that we can replace the worn out pantograph strips during the trip check inspection without taking extra time for the changing the strips. In case we had decided to keep the material of contact wire of a softer material, then in case I want to do any maintenance activity on the contact wire, we need the both power block as well as the traffic block, because the staff will be working to attend the contact wire, and it is not possible to run the train at the same time on the same downline or upline. It is not advisable that for the maintenance activity we restore to regular maintenance activity, or we ask for the regular maintenance block if some maintenance can be done outside the uh, at a site which is does not affect the regular operation of train. So we decided to go for the pantograph pan strips, which is made up of the carbon graphite. Second equipment that we see on the locomotive is the DJ, that is disjointer or vacuum circuit breaker. When it gets closed or when it remains closed, the OHE power supply, which is collected by the pantograph, it is made available to the main transformer. So during when it is closed in closed condition, it passes on the power supply from one end to other side of the circuit breaker. It also has a feature that it opens automatically in case there is an overcurrent or an earth fault in a locomotive. So this is the highest level of protection which is provided in a locomotive. In case of any problem, any earth fault or overcurrent, withdrawal of excess current in the locomotive, it automatically trips off. And the loco pilot, then he carries out some preliminary investigation before he makes attempt to reclose it. And if it gets reclosed, then he performs the journey onward. And if it is tripping again, then he goes into detailed investigation to find out the cause of tripping and to isolate the faulty circuit from the locomotive. The third equipment which is important in electric locomotive is tap changer. The tap changer, it reduces the incoming feeder voltage from 25 kV to 750 volt, which is the requirement for the traction motors in conventional locomotive. They are all DC traction motors. We also need to change the incoming voltage or input to the DC traction motor as per requirement of torque or as per the requirement of the speed. So the 750 volt is the upper limit. There is a possibility that we may require to give a voltage which is less than 750 volts to traction motors. This function is performed by the tap changer. The tap changer is an on-load tap changing arrangement on the primary winding of the locomotive. We have two kind of equipments in electrical engineering. One which can be operated on load, means they can be operated even when the current is passing through them. The other ones are offload equipment, where in order to change the position of a gear or or some switch, we have to ensure that no current is passing through the equipment. So it is not possible to switch off the incoming power supply to loco at a regular interval. So the arrangement is made in such a manner so that it is possible to change the taps even when current is passing through the transformer. We have 32 taps, that is from 1 to 32. A loco pilot can operate the train at any one of those taps. And depending upon the requirement, he either increases the tap to increase the voltage which is going to the traction motor, or he can reduce the tap changer position as per the requirement. By operating it properly, the torque and speed control is achieved by the loco pilot. The output of the tap changer, it is then goes to the rectifier. The rectifier is a device, it's a static device which converts the transformer output from AC to DC, and the after that the power supply can be given to the DC traction motors. When we convert AC into DC, there are a lot of ripples into it, and those ripples are not good for the performance of DC traction motor. The overall efficiency also get reduced, and the life of the DC traction motor also gets affected if there is a lot of fluctuation in the incoming voltage and the current. We use smoothing reactor, and its function is to remove the undulation of the current and to make it as smooth as possible, as close to DC current as possible. So the transformer, tap changer, rectifier, and smoothing inductor. The other components that we have in the traction motor is the transformer traction motors. We have either six traction motors or six traction motors or four traction motors as per the design of the locomotive. They are all mounted under the loco. They are mounted on the bogie, and we have in addition to the mounting arrangement, we also provide safety chains, which also ensure that if there is a breakage in the mounting arrangement, the traction motor does not fall on the track. Any failure of the if the traction motor falls on the track, it is bound to cause derailment. There is no doubt about it. So we have safety chains which take care of the detachment of locomotive from its mounting arrangement, and the entire weight is taken care of by the safety chains which are also provided. The Arno or static inverter unit that is there, which is one which converts the auxiliary winding. It is connected to the auxiliary winding of the transformer, and it converts single phase 440 volt or 400 volt AC supply to three phase AC supply, which is required for auxiliary machines in the locomotive. In the subsequent slide, I will explain the what are the different auxiliary machines which are there in the locomotive, and what are their role and the function in the overall system of working. So as of now, we have earlier it was not a static unit. We had a rotary machine which was converting single phase to three phase power supply, and the it was one of those areas which required a lot of maintenance activity. There were a lot of failures in Arno converter, and even at the Unbalance in the mounting arrangement used to result in a failure. In case the Arno converter fails, none of the auxiliary machines can work in the locomotive, and even if the entire power circuit is working, the loco is declared dead. We cannot operate the locomotive if the Arno converter fails to convert a single phase AC supply to three-phase AC supply. So the reliability of Arno converter was very important, and later on, when the technology got developed, we got rid of Arno converter and we replaced all the Arno converter with the static inverter, which is a now microprocessor based systems which are provided in the locomotive. We have the different auxiliary machines, and the primary function of auxiliary machine is to supply compressed air and to provide cooling for different electrical equipments which get heated up during the journey. The journey may be more than 24 hours, and the traction motors and the transformer, they have to remain on throughout the journey. And during the operation, their temperature becomes very high, and we need some external mechanism, some forced air kind of a mechanism to keep the temperature under control. As per the rule, the overall temperature should not go beyond 80 degrees centigrade. So efforts are made so as to design the auxiliary machines so that sufficient amount of fresh air it is blown over those equipments which are getting heated during the service. The compressor is the first one and the most important of the auxiliary machines. It provide compressed air for all pneumatic operations which are required by the locomotive. The compressed air, it is used for electro-pneumatic contactors. We have large number of electro-pneumatic contactors to switch on and switch off different circuits, including traction motors. We operate electro-pneumatic contactor to put a traction motor in service, and we can also remove a traction motor from service if there is any problem in the traction motor. The circuit breaker, we also need compressed air for the mechanism to operate, and we need compressed air to raise and lower the pantograph. Then the operation of the tap changer servo motor, which has 32 taps. The horns, wipers, sanders, and the air brakes, all of them, they require compressed air. We have either two compressors or three compressors in a locomotive as per the design, and they also work throughout the journey. These are some other auxiliary machines which play their role in the locomotive. I will only talk about the baby compressor. The baby compressor is a very important equipment. It's very small in size, but its function is useful at the time of switching on or starting the locomotive. When the loco is dead, I cannot have the compressed air in the locomotive. So we have a small compressor which can work on the battery. And when the power supply to this baby compressor is given from the battery, the loco pilot, he switches on the power supply and he builds the pressure up to 7 to 8 kg so that the pantograph can be raised and the pantograph can make the contact with the contact wire. Once the pantograph is raised and it has made the contact with the contact wire, the driver, the loco pilot, he closes the DJ. And once the DJ is closed, the power supply is then available to transformer and through transformer to different equipments, and the loco gets charged. Once the loco gets charged, we switch off the power supply which is there to the baby compressor, and baby compressor is not used during the journey till we lower the pantograph again somewhere. So baby compressor, it has an important role and it is to be kept in working condition. There are different auxiliaries which are designed to cool different components and the equipments which are there in the locomotive. The first one is the traction motor blower, and it is known as MVMT. The other one is the smoothing reactor blower, the rectifier blower, and the oil pump. The oil pump is again very important equipment in the locomotive, and again its failure causes the loco to be declared dead. The the function, it performs the function that it withdraws hot oil from the transformer. It then it makes it pass through the radiator tubes. Then on top of the radiator tube, we blow the air through radiator blower, and the in the process, the transformer oil, it gets cooled. And after that, the transformer is again pushed into the transformer. So this cycle remains in service throughout the service. And we keep on rotating the transformer oil using oil pump. It's a closed system. It means that the transformer oil does not come in contact with the external environment, and it is required so that the transformer oil does not absorb the moisture. Any absorption of moisture will reduce the breakdown voltage and the transformer may break. The other function of the transformer, the oil, is that it ensures that the temperature of the transformer oil does not go above the flash point of transformer oil, which is anyway very high. Because any fire incidents in transformer oil, it is very difficult to control, because we have a huge quantity of transformer oil which is in the locomotive, and since the amount of heat which is generated, it makes it very difficult for the fire tenders to control the fire. Therefore, the function of MPH is critical, and its maintenance is also being ensured by some of the best staff which is available in the loco shed. When you people are going to get posted, you will have the choice to put different people in a different job. You may find that the staff of same grade is not capable to do some very critical activity. It is the responsibility of the senior supervisors and especially of the junior scale officers to identify the people who are very good at job, and they should always be given a duty which is related to an area which is critical to us, critical to maintain the safety of the operation, and which is critical to ensure that the traffic does not get disrupted because of some problem in the maintenance activity. Yes, you can, some people will say that the person is getting punished for his efficiency, but that is how the entire world works. The people who are efficient, they are always given the responsibilities, higher responsibilities as compared to the people who are not efficient. And I don't think you will be able to change this rule. This is something which is a well established rule in the society, and it works both in government organization and it also works in the private organization. The other important equipment that we have is the battery. We have a lot of other protective devices. The relays are the protective devices. We have different control circuits and the power circuits. Each control circuit and each power circuit, it is taken care of by one or two relays. And in case there is any problem, the circuit gets isolated from the system. I will now try to show a very small brief animation, and I will try to explain the overall function, whatever that we have discussed today. We have the OHE on top, and when the pantograph is raised using the services of KB compressor, and the moment pantograph makes the contact with the OHE, even before the DJ is closed by the loco pilot, the entire roof of the locomotive is charged by 25 kV. In case there is any requirement by any of you during your service to go on top of the loco for any investigation or for any maintenance activity, please make sure that the pantograph is in lowered condition. Only if the pantograph is in lowered condition, please go on top of the roof, but otherwise don't climb there. There have been incidences in past where the staff, especially in the loco shifts, got electrocuted because the pantograph was raised, or it made the contact and the overhead supply was available on the roof, or when the maintenance activity was being carried out, somebody he switched on the power supply to the roof, which was otherwise isolated for the maintenance activity. We find that the carelessness on part of somebody, it may be fatal for their colleague employees. So let me make it very clear that the pantograph is charged even when the DJ is not closed. Once the DJ gets closed, the power supply gets extended to the transformer, from the primary of the transformer gets charged, and the power supply from the secondary winding, it goes to the traction motor through the rectifier and um, sorry. So this is the overall basic circuit. We have already seen the function of all the uh, equipments which are mentioned in this slide. Here I have shown only one pantograph, but in practice, a locomotive has two pantographs. On each side of on top of each cab, we have one locomotive. And during the service, the rear pantograph is being raised. When I'm moving, say, in the right direction, the rear pantograph is being raised as a practice, and it is done purposefully. Suppose when I'm moving in the forward direction, suppose the direction of motion of the locomotive is the away from the left side of my screen, and the front pantograph is raised. Suppose there is some panto entanglement or some foreign material which has fallen on the locomotive, and in that process, if it has damaged the pantograph, all the other equipments which are provided in the roof, they will also get damaged because the train is moving in the forward direction, and the defective components, they will fall behind the original location of the pantograph. This will make it impossible for the loco pilot to raise the rear pantograph and take the train forward, because that pantograph is also damaged. And the loco is supposed to be declared dead, and then we will provide some assisting diesel locomotive or electric locomotive to clear the section. Whereas if I use a rear pantograph, and if there is any panto entanglement of some damage to pantograph for any reason, then the defective components or defective parts of the pantograph, they do not fall on the locomotive, they fall on the next coach, on top of the next coach, and finally they come down on the side, from the side to the track, and the train can pass through. Therefore, it is a written instructions to the loco pilot that during service, unless until there is an emergency, he should operate the train using the rear pantograph, and he should not use the front pantograph. So we have two pantographs in each locomotive. We have, this is the block diagram for the locomotive, and uh, the OHE pantograph, the power supply comes 25 kV power supply is passed to the transformer, primary side of the transformer. We have two secondary windings. One secondary winding is connected to one rectifier block and its associated smoothing reactor. And the power supply is then goes to three traction motors, which are provided in one bogie, assuming that it's a COCO kind of a locomotive. So one secondary winding takes care of one set or one bogie, or the traction motors which are provided in one bogie. Similar arrangement is available for the other secondary winding. We also have auxiliary winding. The output is given to the Arno converter, which converts single phase to three phase, and the power supply then goes to all the auxiliary machines. I have used different color code to indicate different voltage ratings that are available at a different part of the entire circuit. It is possible for the loco pilot to isolate one traction motor at a time. He can also isolate all the three traction motors of one bogie. So it is possible that I can isolate traction motor, any traction motor at one time. The circuits are designed in such a manner that all the circuits, they work parallelly independent of each other. The cost is something which is to be discussed. We have large number of locomotives, more than 11,700 locomotives in service. As on date, an electric locomotive, it costs somewhere around 14 to 15 crores of rupees to manufacture at CLW or at DLW. One of the parameter which is always considered as part of the design of electric or diesel locomotive is specific energy consumption. It is the most appropriate parameter which is to be measured to design or to decide the efficiency of the locomotive. For it is defined as kilowatt hour per 1000 GTKM. For the goods train, it is 8 kilowatt hour, and for passenger train, it is 19 kilowatt hour. The requirement of specific energy consumption (SEC) is more for the passenger train because we are running or moving the passenger trains. Means when I write passenger trains, it means all mail express and superfast trains, say at the speed of 130 or 140 kmph. It requires more specific energy consumption as compared to the goods train. There are different protection devices which are available in the form of relays in the locomotives. I have mentioned some of them here. It is for the high current in main transformer winding, over current in silicon rectifier, over voltage protection, low voltage protection, which is also there. The low voltage protection is also provided in the locomotive. The locomotive is designed in such a manner that in case the OHE voltage goes below 19 kV, then the entire loco gets stripped off because it cannot work optimally, or it cannot work. We have no voltage or low voltage protection, which actually sends the voltage which is available from OHE, the voltage level which is available from the OHE. Then we have auxiliary power circuit earth fault. Each auxiliary machine, it has its own earth fault protection system. And when there is an earth fault, we have to isolate that particular auxiliary, and along with the auxiliary, we also have to isolate the power circuit. So we have the both the protections, they go hand in hand. The protection of the power circuit and the protection of the auxiliary circuit in a locomotive. There were certain shortcomings of DC traction motor. We had discussed the shortcomings of self-generating system. Similarly, we also had certain shortcomings when we were using DC traction motor, and that is why the decision has been taken to stop manufacturing any locomotive using DC traction motor anymore. Now, all the new locomotives, they are using three-phase technology for the traction purpose. The existing design of the DC drive locomotive, it is capable to give power up to 5,000 horsepower. It is because of the space constraint that we have in the locomotive, and within the available space, the maximum permissible size of the DC traction motor, which can easily be fitted, can only generate power up to 5,000 horsepower. So that was the upper limit. In case we want to have a locomotive with higher than this rating, then it was not possible to manufacture that locomotive. There were unavoidable step jumps whenever the loco pilot moves a tab from 1 to 32. The, there are jumps in the entire traction system, and these jugs can also be filled by the passengers if the steps are taken very quickly before the speed gets stabilized, or before a certain if the transient time is very less. Suppose he moves 10 notches at one time, immediately one after another, and the transition time is less, then the passengers will definitely feel the jerks. The DC traction motor, it has the inherent problem for brush tear and the commutator, and they are maintenance intensive. And essentially, the DC motors, they are high current, low voltage machines because they operate at 750 volt. And in order to have 500 horsepower, the requirement of current is very high. Whenever we have higher requirement of current, it means that the size of the cable is high, and the cable becomes heavy, and they also become expensive because we are using more copper to manufacture those cables. The DC motors, they had this disadvantage, and and if you see, if you ever go inside the locomotive when it is in a strip condition, the entire locomotive is covered the different kind of cables. You will find there is a huge mesh which is there in the locomotive, and the cables, the power cables and the control cables, they are placed in the locomotive. Let us now talk about the three-phase locomotive. That is the new design, and future belongs to three-phase technology. They are they use three-phase induction motors. The advantage of three-phase induction motor that they are compact and high-speed motors. There is no commutation, so there is less maintenance. They are light in weight. It means that the output power per unit weight, per unit dead weight is higher, which makes it ideal for the traction purposes. The high power weight ratio that I have said. There is no moving part because there is no commutator, and there is no restriction of rotation RPM of the motor as there is no commutator. So these are some of the advantages of the three-phase induction motors. These advantages has been exploited to design a system, traction system, by using the three-phase induction motors in the locomotive. The other advantages that we have for the three-phase locomotive is the first one is the regeneration. The regeneration is a mechanism in which during the braking operation, the traction motors they start working as generators. Under the norm in the normal locomotives where we are using DC traction motors, the during the braking operation, the entire kinetic energy it gets converted into heat energy and the friction energy. When there is a when the we press brake block on the rim of the wheel, when the brake blocks are pressing the wheel, they facilitate to reduce the speed, but in that process, the energy gets lost into the environment. In the regeneration process, we have a microprocessor-based control systems which convert the traction motors into generators, and rather than consuming the electricity is now generated. As we do not need that energy for the train because we want to stop the train, the excess energy it goes back to the grid. If it goes back to the grid, we get rebate from the distribution company. And if there is any other train in the vicinity of this particular train, then the energy gets transferred through the contact wire to the other train. We do not require extra energy from the distribution company, and the electricity which is generated in three-phase locomotive, it is given to the another locomotive. By using this technology, we are in a position to save somewhere around 20 to 30% of the energy cost. We can have increased starting tractive effort and increased horsepower because it is possible to have variable voltage and variable frequency drive, and that it makes it possible to have variable tractive efforts and variable horsepower at the time of start and during the run of the locomotive. We have microprocessor-based self-diagnostic system in the locomotive, which keeps on recording the vital parameters of the locomotive. And at the same time, in case there is any failure in any of the circuits or in any of the equipment, a message gets flashed at the driver's desk, along with the remedial action which can be initiated by the loco pilot. It makes the life of the loco pilots slightly comfortable because he does not have to search for the location of where the fault has occurred, and he can immediately go to the location which is suggested by the diagnostic system, and he can take the corrective action and clear the section. This is how the three-phase locomotive looks like. The block diagram, basic block diagram of a three-phase locomotive. We have the transformer, and the output of the transformer it is given to a converter which converts AC to DC, and after that the power supply it goes to the DC link. DC link is nothing but the capacitors, series tune filters, and some of the protection devices which are there and which form the entire circuit in the DC link. The primary function of the DC link is to act as the reservoir of energy, which supplies periodic or non-periodic energy requirement of the load and decouples it from the power source. Suppose in case I want to slow down the train, the energy comes back to locomotive, and rather than using the brake block, we control the overall energy which is available in the traction motor, and we store the excess energy in the DC link. And in case we want to increase the speed, rather than taking the power from the distribution company, the stored energy in the DC link, it is given to the traction motor. This cycle, it keeps on going during the run, and we save some energy by using DC link also in the locomotive. The output is given to a voltage source inverter. There are two types of inverter in electrical engineering. One is the current source inverter, where the input current remains constant, and we have voltage source inverter in which the input voltage remains constant. The output of this inverter is a three-phase AC supply, and the magnitude and the frequency of the voltage can also be changed. The output voltage can be from 0 to 2180 volt, or output can be from 0 to 160 hertz. So it's a variable voltage, variable frequency device drive, which then is then given to the traction motor, and the required active effort is passed on to the traction motor and to the wheels at a later stage. So these are the basic building blocks which are being used in any three-phase system. It can be a three-phase locomotive, it can be three-phase electrical multiple unit, or a three-phase mainline electrical multiple unit. The basic building block, they remain same, and their interaction also remains same. It is the only the variation in the ratings and the location of the equipments in the system which is different depending upon whether it is there on the locomotive or it is provided in the EMU. This is how the entire system looks like. We have the OHE. I have shown only one pantograph, although we have two pantographs. Circuit breaker, the main rectifier, then the power supply, power comes to the transformer. Through main rectifier, it goes to the inverters through the DC links, and the output three-phase power supply, it is then given to the AC traction motors. We also have one auxiliary inverter which converts the voltage to the required level for operation of the three-phase auxiliary motor machines. We also have the battery, and in order to charge the battery, we use auxiliary rectifier, in which the input power supply, it comes from the auxiliary inverter. So auxiliary inverter has two functions: to provide the incoming input to power supply to the auxiliary machine, and also to charge the rectifier. When we have more than 11,000 locomotives and the reliability is important, we have laid down maintenance practices in the for the locomotives, and each locomotive is nominated to one of the loco sheds that we have on Indian Railway. Each loco, it is assigned because the all the primary maintenance, all the scheduled maintenance, which are other than the failures online, they have to be carried out by the nominated loco shed. The during all the modifications which have been issued by RDSO after the locomotive was manufactured in CLW, all such modifications have to be carried out by the nominated loco sheds. Suppose a locomotive has been released, or it was manufactured in 2018, and the RDSO has issued a modification sheet. It can be based on some technical development, or maybe because of a newer design of component is made available in the market, or there were a large number of failures in a particular design. It can be either one of these situations, and a modification sheet is issued by RDSO, and the activities are also mentioned about what are modifications have to be carried out in the locomotive. All such modification sheets, they have to be implemented by the loco sheds as and when the loco touches the homing loco shed. The maintenance work should be there. We have some laid down maintenance activities which have to be carried out, and along with those maintenance activities, all these smaller complaints which have been recorded by the loco pilot in the logbook, they are also attended during the uh, maintenance which is carried out in the loco shed. The history of equipment and maintenance is also important in order to make sure that no equipment remains in the locomotive which is overdue for replacement. A proper history is maintained in the database which is available with the planning organization in the loco shed. The component or the equipments, when they are where they have completed their total life, they are removed from the locomotive and they are scrapped, and we provide new components in lieu of the scrap components. Similarly, the maintain what all maintenance activities, the major maintenance activities which were performed on the locomotive during the last visit, they are also get recorded in the database, and it also gives a clue as to what are the different areas which are demanding regular maintenance in a particular locomotive. Each locomotive is identical as far as design is there, but each locomotive, it behaves independently, independent of the behavior of other locomotives. So it is important to know which area or which components are critical and which are failure prone components in a particular locomotive. So whenever the maintenance activity is performed, the history of the prior history, or history is always prior, the history of the locomotive, history of the equipment, it is always taken into account. The frequency of maintenance, there are different schedules which are prescribed for the locomotive. TI is the trip inspection, and it is being performed outside the outside the loco shed. The trip inspection is one activity which is performed at the trip sheds, which are under the control of PRO organization. And we have trip sheds at all major stations where large number of trains get terminated after the journey. So trip activity, or among all the scheduled maintenance activity which I have listed over here, the TI activity is being carried out at the trip check. POH activity is carried out at the POH shop, which is again a dedicated unit. Other than trip inspection and POH activity, all other scheduled maintenance activities, which are five in number, IA, IB, IC, AOH, and IOH, these activities, they are being performed in the loco shed. AOH means annual overhaul. Traditionally, it was called annual overhaul because the activity was performed at an interval of 12 months. Now we have increased the periodicity from 12 months to 18 months, but the name AOHS is still being used by Indian Railway. Intermediate overhaul is something which comes in between AOH and POH. And then we have IA, IB, and IC schedule. Earlier, they were called monthly schedule because the periodicity of for IA was 30 days, for IB it was 60 days, and for IC it was 90 days. So after every 30 days, the loco was coming to the homing loco shed for the regular maintenance activity. When the technology got established and when we moved from the DC technology to AC technology, we increased the periodicity of the maintenance also. As we can see that in a WAG9 locomotive, the IC schedule is being carried out after an interval of 270 days, whereas an IC schedule in a WAG5 locomotive, it is being carried out at the interval of 135 days. So the maintenance in a three-phase locomotive is much less as compared to maintenance in the conventional locomotive. There are different variants in the WAG9 locomotive, which is which till now was the locomotive, goods locomotive with highest horsepower available to it. It was 6,000 horsepower which was available. Now we have also come out with a new locomotive, WAG9 locomotive, which has 9,000 horsepower of the capacity, and it will be used primarily for the dedicated freight corridor. We started with the GTO thyristor technology in the power circuits, and since the IGBT technology is superior than the GTO technology, we later on moved into the IGBT technology, and now all new locomotives, they are being released with the IGBT based system. The latest locomotive that I would like to talk about is WAG12 locomotive. It has been dedicated by Honorable Prime Minister during the April this financial year. So far, we have released only 2 or 3 such locomotives for service. It's a three-phase locomotive with a BO plus BO kind of a configuration. There are 2 units, and each unit is having a BO kind of an arrangement. They are coupled together, and we are manufacturing 110 locomotives per annum. The Initially, these locomotives, they will also be used in dedicated freight corridor to haul heavier loads, and they are going to be used for dedicated freight corridor because the capacity or the output which can the air from the locomotive is 12,000 horsepower. So far, we had no locomotive in our service with us in our fleet, which can generate 12,000 horsepower of power. This is the locomotive which is going to generate 12,000 horsepower, which is twice as much as the immediate predecessor, which is WG9 locomotive. It is being developed with Alstom and Indian Railway, and it is one of the most powerful freight locomotive that we have on Indian Railway. The production has already started, and we are going to, increase the production from this financial year itself. So this is all that I wanted to talk about the electric locomotive. I will now close this part of the presentation, and I will start the next part of the presentation, which is related to TRD organization. So give me 2 minutes so that I can change the slides from presentation from this presentation to next presentation. So let us begin the next presentation, that is TRD. TRD has 4 functions to perform on regular basis. First one is to provide the reliable power supply for electric locomotive. Second one is to coordinate with traffic department to take power blocks for to carry out maintenance activity on overhead equipment or in the power supply equipment. We have to coordinate with the RO department to for the some trial runs or to operate the tower wagons and to carry out investigation in case there is any failure of the locomotive. Then they also have to carry out some joint examination so that no OHE mast should infringe the visibility of the loco pilot. There is a possibility that when the loco pilot is operating a train or driving a train, and if it's a newly constructed ERD section, the location of the OHE mast may infringe the visibility of the loco pilot. When such matter gets reported, the DRO and TRD organization, they carry out joint footplate inspection along with the S&T officers to make sure that the visibility, either the signal gets relocated or TRD marks gets relocated so that the visibility to the loco pilot is ensured as per the laid down norms of visibility. The third one is the to coordinate with the adjoining railway. We have a physical demarcation of each and every division where the jurisdiction of the division ends and the jurisdiction of the next division starts. In case of TRD, we take the incoming power supply at every 60, at the interval of every 60 kilometers. So there is a possibility that we have taken the power supply in one division, and some portion of the feeding zone or some feeding zone of the TRD, it lies in the adjoining division. So in case any power block is to be taken or some maintenance activity is to be carried out on a section which is falling in the jurisdiction of adjoining division, then TRD has to coordinate with the adjoining division to allow them to carry out the maintenance activity. And the fourth one, which is very important, that you have to coordinate with the state electricity board for uninterrupted power supply, for issues related to billing cycle, for the tariff, and they all have also got to coordinate with the state electricity board to project the requirement of electricity which is there for the train operation. In case the requirement is more, then we have to inform the state electricity board for providing us the extra power. We have a concept of scheduling the power. There are state load dispatch centers, and there are some other organization in the state organization which have to be consulted at regular interval to make sure that the power supply is available on uninterrupted basis to Indian Railway. So these are the four major functions which are performed by TRD organization. These are three different wings: OH wing, power supply wing, and the RCC wing that we have already seen earlier when I introduced the electrical engineering department to the class in my very first session, which I took with you. The traction system, earlier we were using overhead 600 volt to 3000 volt DC system, and that system was being used because all over the world this was the only system which was used for the electric traction purpose. The concept of AC traction was not there. The 1500 volt DC system, it was introduced in 1925 in India. The third rail collection system is a popular system for the metro railways where the voltage is from between 600 to 750 volts. And in India, when things became better, the technology got developed, and the different countries they starting phasing out the DC traction system from their system. We also switched over to AC traction. That was the one reason. There are other advantages of AC traction that I'll explain in the subsequent slide. There is a question: who will be the reporting authority for loco pilot? Is it senior D or senior DME or senior DCM? Is there any segregation like diesel loco pilot and electric loco pilot? Okay, the question has come from Anudeep. The we Senior DCM, nobody reports to senior DCM, that is for sure. But in the non-electrified territory where we do not have the electric locomotive, the loco pilots they report to senior DME. In the electrified territory where we had both electric locomotive as well as diesel locomotive, prior to 2016, the loco pilots of electric locomotive were reporting to senior D, and loco pilots of diesel locomotive they were reporting to senior DME. In 2016, the reorganization of electrical department and mechanical department took place, and the all the diesel locomotives they were also they were also became part and parcel of the electrical department. It means it became the responsibility of electrical department to maintain diesel locomotive along with the electric locomotives. When this got implemented, the loco pilots who were earlier driving the diesel locomotives, they also started reporting to the TRO organization of electrical department. At the same time, when the additional responsibility of diesel locomotive was transferred from mechanical department to electrical department, the primary responsibility of maintenance and operation of electrical multiple units and mainline electrical multiple unit, it was transferred from electrical department to mechanical department. And accordingly, some of the officers, electrical officers who were working for the maintenance and maintenance of the EMU, now they are reporting to PCME. So we have an arrangement now in Indian Railway where the mechanical officers who are posted in the loco sheds, diesel loco sheds, they are, although they are IRSME, they are reporting to PCEE. And we also have some of the electrical officers who are IRSEE, and they are maintaining the EMUs. Now they are reporting to PCME. So there's that dual arrangement is already there. Each segregation, it was there earlier because the diesel loco pilot and the electric loco pilots, they were totally different cadre. It was a totally different cadre under two different departments. So, and they were not allowed to operate the other type of the vehicle. The loco diesel loco pilot was never asked to you drive a electric loco pilot and vice versa. So the no technical knowledge was imparted to either of these set. Now, all the new loco pilots who are joining Indian Railways, they are being trained to pilot both diesel locomotive as well as the electric locomotives. The training has been reorganized in such a manner that the training is being given to both the territories. The other difference is that we had a good fleet of the diesel loco pilots, and as the electrification is progressing in Indian Railway, the requirement for electric traction based trains is continuously increasing in the division. And since there is no vacancy or there are less number of vacancies because we have diesel loco pilots, so we made a plan to arrange refresher course for all these diesel loco pilots. They were also trained to drive the electric locomotives. They underwent some training, some simulation based training, and they are now quite capable to derive even electric locomotives. So earlier there was a segregation, but now there is no segregation. These are some of the advantages that we have for the 25 kV OHE. The first one is the regulated OHE. When we say that OHE is regulated, we mean to say that the tension which is available in the contact wire and the catenary wire, it automatically taken care of by some mechanism which is provided at both end of the OHE. During the summer season, the OHE, since it is made up of copper component, it gets elongated, and there is a sag which gets developed in the OHE. This sag is not good for the smooth transition of the or is for the proper contact between OHE and the pantograph. As the sag, it will hamper the speed at which the train can negotiate the OHE. And if the sag is very high, then the pantograph will also hit the OHE from the side, and it may damage either the pantograph strip or the contact wire. Therefore, we have some arrangement through which we can control the overall tension which is supposed to be maintained in the OHE. And such OHE is known as regulated OHE. It's a primary concept or a basic concept for the AC traction, and it makes it possible to operate trains at a higher speed, and the failures are also less because there is no snapping of the contact wire because of the interaction between the contact wire and the pantograph. We can run longer and heavier trains because the current carrying capacity of the OHE system, which is available in 25 kV AC, is much higher than the OHE, which is used in 1500 volt DC. As we have more current carrying capacity, we can draw more power from the OHE, and heavier load or the faster trains can be made operational. 25 kV 50 hertz OHE system is universal in most of the countries now, and there are a lot of industries who are manufacturing the components and the entire assembly to be provided in different parts of the world. Almost all the fittings, they are standard as far as the drawings and the dimensions are concerned. So the availability of spare components for operation and maintenance and even for the new construction activity is available to us. So the concept of standard fitting, it has also helped Indian Railway to increase the electrification at a higher pace. The reduced requirement of copper, this I have already discussed when we discussed the advantages of three-phase locomotive. What happens when we increase the voltage? If we increase the voltage, the current requirement goes low, and when we have less current requirement, the size of the cable, it also becomes less. So the same principle, it is applicable in TRD also. The other advantage is the increased spacing between two adjacent traction substation. Whenever we want to construct substation, we have to offer the land for the erection of the substation. Land is a critical issue when we want to have or construct a substation in major cities. All along on either side of our tracks, large number of multiplexes and the residential complexes, they have come up, and some of the major roads, they are also there on both sides of the tracks. It makes it impossible, next to impossible to acquire the land for the construction of the substation. That is one aspect, the constraint of acquiring the land for construction of substation. The second constraint is that if I have more number of substations, the maintenance requirement will also go high. So we always prefer to have less number of traction substation in the system. Give me a minute. Sorry for the interruption. We can have uh, spacing at the interval of 50 to 60 kmph as compared to 8 to 10 kilometers for the DC traction. Imagine the number of DC substations that we have to attend in Mumbai area or in Kolkata area. The spacing was less because the current carrying capacity for the conductor or the total amount of power which we can draw from the DC traction substation was less. And as and when the number of trains increased, the power requirement also increased. And sometimes it happened that we could not run adequate number of trains because there was a restriction from the DC traction. Yes. We have two types of current collection system for the traction purposes. One is the overhead system. The other one is the third rail collection system. Let us briefly see the difference between both of them. In the overhead system, the overhead conductor, they are suspended above the rolling stock, and vehicle, it collects the current using collects the power. Current is the loose word. It collects the power from the pantograph. Then pantograph, we have already discussed about the pantograph. In the third rail collection system, there is additional rail which is provided on the side of the track. It collects power through third rail, which is supported on the insulator. It is the preferred mode of collection in metro railways. So wherever we need, wherever we are going for the metro railway, we prefer to have third rail of kind of an arrangement. And wherever we have the tunnels or underground system, there also we prefer to have third rail collection system. The traction power supply, I will now explain how the traction power is made available to electric locomotive and how we ensure that the electrical power supply is available from one part of the country to another part of the country, and why train does not stop when it moves from from the jurisdiction of one state to another state, and why we don't feel why we feel that the power supply is continuously available and there is no break or nothing in between. We feel as if we have a continuous power supply throughout the system, but in practical situation, it is not like that. We have divided the entire power supply into different smaller sections, smaller zones, to for the sake of isolating a smaller section for the maintenance purposes. I will explain how have we designed the entire system so that we can have smooth operation and continuous availability of the power supply to locomotive. The power supply, it is always taken at 66 kV and above from the state electricity board. We always prefer to take it at a higher voltage. We are now insisting that we should get the incoming power supply at 400 kV. The reason is as per their maintenance activity. Suppose because of any reason, the distribution company has to impose some kind of power shedding in a colony or in a city. Then the first casualty will be the residential colonies because we operate at 440 volt. The second casualty, the next higher level of the casualty is the market area, where they switch off the power supply. Suppose the power cut is even has a requirement which cannot be met by disconnecting the power supply to the residential colony and to the shopping area, then they switch off the power supply at 33 kV. And to 33 kV, the power supply to the manufacturing units and in some of the SEG zones, they get extended. In case there is further requirement of power cut, all those consumers who are connected to 66 kV, they will be disconnected from the system. So this is how the grading of the disconnection of the power supply it takes place in the distribution company. The 400 kV power supply it gets extended from one state to another state. Normally, more than two states are connected to 400 kV power system. The interruptions are far few, or there are hardly any interruption during the entire year, and they also have alternate arrangement, a ring band kind of an arrangement, so that they can also provide supply from the alternate source of power supply. So we are now insisting that we should be given or we should be allowed to get connected to 400 kV network. And if the distribution companies don't agree, then we now insist that we will not go below 220 kV system. So now all new traction substations which are coming in Indian Railway, they are either connected to 220 kV system or they are connected to they are connected to 400 kV system. There are again what I discussed when we had discussion on the power supply which is given to the railway station. We have followed the same principle for the power supply that is being made available to our traction substation. We take two independent circuits from the distribution company so that in case they want to carry out maintenance on one of the transmission line system, the power supply is available from the other source of distribution company. So we always take two independent incoming power supply from the distribution company. The adjacent TSSs, they are on different phases. Now the TSS, they have two numbers of transformers. The minimum rating is 12.5 MVA and the maximum rating which is available right now on Indian Railway is 30 MVA power transformer. The dedicated freight corridor, they are using 60 MVA power transformers in their substations. The incoming voltage steps down. One of the two transformer, it remains in service. The other transformer is 100% standby. We are using only one transformer at a time, and the other transformer takes over when we want to do some maintenance on the transformer which is in service. So we have two independent incoming power supply and arrangement, and we also have two independent transformers to take care of the load. This is how the general power supply arrangement looks like in the TRD system. Here in this particular screen, I have shown three TSS, TSS1, TSS2, and TSS3. The transformer which I mentioned is 132 by 25 kV transformer, and the incoming power supply is connected to independent three different phases before extending the power supply to Indian Railway. The power supply from one TSS cannot go endlessly to the other side of the country. It has a limit beyond which we cannot extend the power supply. There, the primary requirement is the voltage drop, which is there at the other end of the system. Suppose normally we have the feeding zone. The normal feeding zone is of 60 kilometer. It is 30 kilometer on either side of of the TSS. It means the TSS is situated in the middle of its feeding zone. It feeds 30 kilometer on one side and 30 kilometer on the other side. In between the feeding zone of two TSS, we have a small section. Now it is only 5 meter long, where in which we have no electricity available in the section. We only have the mechanical continuity in that section, and the locomotive, it slides over from one side of the system to the other side of the neutral section. This location is known as the location of neutral section, and this location is also known as SP, that I will explain in the subsequent slide. So for the time being, you please understand the concept of the neutral section, that it acts as a delimiter, and it stops the power supply of one TSS, which can be extended on the other side. Suppose I have taken my own TSS for maintenance. Suppose because there are maintenance schedule similar to the loco maintenance schedule, when I have to shut down the power supply in the TSS and have to carry out the maintenance in the TSS. When I take the TSS into for the maintenance, the power supply in its feeding zone, it's not available. But I should have some alternative arrangement to feed the OHE, because I have not taken the maintenance block in the OHE. So if I have not taken the maintenance block in the OHE, I should be in a position to extend the power supply from the adjoining TSS. When I want to do it, we have a bridging interrupter, we have a bridging mechanism which is provided at the neutral section. And when we operate that bridging mechanism or the bridging interrupter, the power supply from TSS1, it gets extended to power feeding zone of TSS2. So that is another feature or another function which is performed at the location where we have the neutral section. There are three types of switches which control the power supply. First one is circuit breaker, interrupter, and the isolator. I will briefly tell the difference between these three types of control switches. The circuit breaker, it is used or close or open the electric circuits. It can be operated remotely from the control room. That is the advantage of using circuit breaker. And it opens automatically under abnormal conditions. So these are the three key features which distinguish circuit breaker from the interrupter. And wherever we have a requirement from safety point of view, so to isolate a faulty circuit, we go for circuit breaker in the design. Interrupter is a different switching device. It is a switch which can be remotely operated, but it does not have the ability to operate automatically, and it does not get tripped automatically on its own under faulty conditions. Now let us see how the interrupter works at the insulated overlap. When the interrupter is not closed, the OHE is restricted to the left hand side of the interrupter. It does not get extended on the other side of the OHE. Suppose I want to extend the OHE from left hand side of the screen to right hand side of the screen, then we close the interrupter and the power supply gets extended on the other side. This function is also performed when I want to extend the power supply from one TSS to other TSS. When I switch off the interrupter, the power supply which was extended earlier, it is no longer available on the other side, and the normalcy gets restored. So this is how the interrupter it is operated in the system. The third function, third switch which is available to us is the isolator. It is the most elementary switch which is there in the TRD system on Indian Railway. It can be operated manually, so that is how it distinguishes itself from the interrupter and from the circuit breaker. It can be used to isolate the smallest section. It can be a single tension length. The single tension length of the OT is 1.5 meter, so it can be used to isolate a very small section. It is normally provided in the yards to isolate one of the loop lines or the stabling lines, and it can be operated only when low current is flowing through it. It means it is a no load kind of a device. We have to ensure that no current is flowing through it. When I operate, there is a concept of padlock, which is a unique feature which we have provided here on Indian Railway to ensure safety of the manpower. Whenever we want to isolate the power supply, there is a padlock which is there is a lever which is provided at the foot of the mast on which the entire isolating assembly is mounted. The maintenance staff they can operate this uh, lever, and when it gets rotated by 180 degree the isolator opens and the circuit gets isolated. Now the role of the padlocks comes here. It's very easy to operate. The lever is very easy to operate. Once I operate it by 180 degrees, I am supposed to lock it in its position so that nobody else can operate it again accidentally without taking into cognizance that some maintenance activity is being carried out. And there are maintenance staff who are actually touching the contact wire or replacing or attending some fittings that are provided in OHE. Some accidents have taken place in past where the lever was operated in the normal position and the maintenance staff they were electrocuted. So it's the responsibility of the OHE maintenance staff to ensure this basic principle, and it is already laid down in the work instructions which are issued to TRD staff. Let us see how the isolator work and how it isolates the system. This is the normal system. The current is available or the power is available in all the lines which are marked with the red color. I am only showing the downline because we have independent circuit for the downline and the circuit for the upline is independent of the circuit which is there in the downline. Under the normal circumstances, the power is available to main line, loop line, and all the other stabling lines. Suppose I want to disconnect the stabling line and I want to switch off the power supply which is available in the stabling line, then I'll operate the isolator. And I have called it the abnormal condition because I am disconnecting the power supply for a particular line in the yard. The moment I open the isolator, the power supply which is available to the stabling line, it gets disconnected and now the maintenance activity can be performed. So this is the function of isolator. Let us see the overall functioning of the TRD system. We get the power supply at 66 kV and above. After the stepping down using the power transformer, the output voltage is at 25 kV. Then we have the first circuit breaker, which is the low voltage circuit breaker. The function of the circuit breaker is to sense the incoming voltage, the level of voltage, incoming level of the voltage. In case if it is found that the incoming voltage is very less, then the circuit breaker will not get closed and the no power supply will get extended to the OHE system. Only when the power supply, incoming power supply is within a range, then the power supply gets extended from the circuit breaker. It comes to the feeder circuit breaker, and from the feeder circuit breaker, the power supply goes through the interrupter to the OHE. From OHE, the power supply gets extended to the pantograph, And from the pantograph, it goes to the transformer, traction motors, to the wheels, and the power it is then comes back to the substation. So this is how the entire circuit gets completed. So I will show you a small animation in which I have tried to show the animation, the flow of the current. When the contact, when you will as in when you will find that the pantograph has made the contact, you will find a sing sound which will come to your mobile or your screen. This is how the entire circuit it works in the electric locomotive. Sorry, in the power supply, which works in the OT system, PRD system, and as well as in the loco system. Whatever that is marked now that constitute part of the OT. The other component, the everything which is there in the yellow box, it is PSI arrangement, and both PSI and OT, it is controlled by the PRD system, by the operators who are manning the remote control center. We have different supply control posts. I will take another 5 minutes before we close the session. We have different supply control post arrangements to section to divide the entire OGA to different sections to improve the maintainability of the system. Section substation we have discussed. We have the feeding post, and I will explain what is a feeding post, sectioning post, and SSP. So these are the four main supply control posts which are there in the OHA system to divide the OHA into different sections. Some of the components that we have in the PSI are mentioned here: circuit breakers, different devices, the potential transformer, the current transformers, relays, and the meters, and other associated devices. Let us see the role of the feeding post. What is the function of the feeding post? The feeding post, it is a location which is located near the track, and it is somewhere in between the OHA system and the traction substation. Once we step down the incoming voltage from 66 kV to 25 kV, we have to extend the power supply to OHA, and that job is performed by the feeding post. So the incoming power supply from the TSS, which is at 25 kV, it comes to the supply post, and the feeder lines, it is terminated here, and from here we connect the incoming power supply to OH. So each feeding post, it has four feeder lines, one feeder line for one direction of either OH, of either upline or of the down. There are feeders on the feeding post, and each feeder supplies the OHE on one side of the feeding post. So it means in a double line section, we have four feeders. This is how it looks like. You can see the boundary wall, and we have the feeding arrangement. The rightmost section, which is the H-pole structure, which is there on the screen, is the feeding post. There are four feeder wires which are getting extended to the OHE. On the left-hand side of the screen is the transformer or the TSS, and on the right side of the screen is the OHE. On the right-hand side of the screen is the OHE and the tracks, upline and the downline. So feeding system is something which is sandwiched between track and the TSS. We also have SP, that is sectioning and paralleling post. It is the location which controls where the power supply gets extended. I have already explained, we have a neutral section which is provided at SP. Then the warning boards are also provided in advance to the loco pilot that he is about to leave the feeding zone of one TSS and he is entering into the feeding zone of the other section. This is the another arrangement that we have in between, because sorry, we are still on SP. I thought we have moved on to SSP. This is the SP. The other function which is performed at SP is that we have a paralleling interrupter, which I explained earlier, which can be switched on to. I'm getting lost. We have a paralleling interrupter. Sorry, I was talking about the bridging interrupter. We have a paralleling interrupter at each SP, which is used to parallel the OHE. Now we have OHE length in one direction of 30 kilometer length, and for the up line, and we have another OHE of 30 kilometer length for the down track. By using the paralleling interrupter, we make both the circuits in parallel. And when we make circuits in parallel, the overall resistance gets reduced, the IER square R losses gets reduced, and I have a better voltage regulation. So paralleling interrupter is something which always remained in working condition, and its primary function is to make the OHE parallel. The second function, which is performed by which is there in the SP, is the bridging interrupter, which is used when I want to extend the power supply from one FP, one side of the TSS to another TSS. Here I have mentioned from one feeding post to next feeding post. Feeding post is something which is in front of the TSS. In addition, we have the sectioning and paralleling post. This is going to be the last slide for the session. It's a supply control post in which we can further divide or subdivide the entire OHE. Here we have the arrangement for paralleling the OHE and for subsectioning the OHE. There are three interrupters which are provided at SP. Two are there to connect the adjoining subsection, because I have to extend the power supply from one section to another section in the SSP. And we have one paralleling interrupter which parallels the up and down track. So these are the different arrangements. In the next session, when I take the session, I will explain it in detail using a diagram as to how these interrupters they work together and they perform their entire function. So that is all.